guys, so we've kind of said De Moivre's theorem. We have about three applications or three uses for this theorem. So one of the first ones, I suppose, is that base level kind of computing powers. The second one is what we're going to look at here, and that's for finding ways of rewriting multiple angle formulas. Now, we might remember from trigonometry, we had formulas like cos 2a or sine 2a, and we had specific kind of identities or formulas that we used for those values that we were able to kind of just use from our log tables. Now, what we're going to look at is ways of using De Moivre's theorems to essentially nearly derive those formulas. So ways of expressing cos n theta in terms of cos theta, sine n theta in terms of sine, or in terms of sine and cosine. And it just depends on what the question asks us for. And that a lot of the time will depend on the power that we're looking at and the value that we're looking at. Now, the three things I've said to remember is sine squared theta plus cosine squared theta is equal to 1. So again, that was one of our identities from trigonometry. It's in our log tables. The next thing is if we have a plus bi equals c plus di, then a must be equal to c and b must be equal to d. So that just means the real parts must be equal and the imaginary parts must be equal on either side of our equal sign. And just making sure that we're kind of aware of those bits. And the last part I've said there then is the binomial theorem can be used in expansions of the form a plus b to the power of n. Now, the binomial theorem obviously is from Algebra 1, and this is, I suppose, one example of where it can come up that's not in that algebra section, that's not in that initial section as its own question. So it can come up as part of this kind of question or as part of these identities. So if we want to express cosine n theta or sine n theta in whatever form they've asked us for, we have to use the fact that we can compute something like this by using De Moivre's theorem or the binomial theorem. And either way that we do it, because we have two ways, they should give us the same answer. So even though we have two methods, we should get the same answer, because it couldn't make sense that we could do it two different ways and get two different answers. It's two different methods to the same end result. So what we're doing is we're going to do it each of those ways, and then we're going to equate our two answers and use that to prove the identities that we're looking for. So let's just see how that works. So we're looking for the first one here. We're looking for sine 4 theta and we're looking for cosine 4 theta. So we're going to be looking at kind of that expansion to the power of 4. So let's just lay it out for ourselves. So we're looking at cos theta plus I sine theta to the power of 4. That's what we're kind of considering here. So let's just look at De Moivre's theorem first of all, and if we were to compute that with De Moivre's theorem, it would become cos 4 theta plus I sine 4 theta. Okay, nice and simple, that's why we like it. The binomial one might be a little bit more hassle for us to remember. So remember that your binomial expansion starts with however many kind of choices or whatever we're looking at. So we're looking at 4, so we start with 4, choose 0. We will start with cos theta to the power of 4. Then we have 4, choose 1. We would have cos theta to the power of 3. And we consider the I sine theta then to the power of 1. We have 4, choose 2. We have cos theta to the power of 2. We have I sine theta to the power of 2. We have 4, choose 3. We have cos theta to the power of 1. We have I sine theta to the power of 3. And then we 4, choose 4, and we have I sine theta to the power of 4. So making sure there as well that we're including those I values in this binomial expansion. So our two terms are cos theta and I sine theta. So we have to make sure we're including that I sine theta as well. And the I suppose, is the easy part to forget. So let's just work through. So 4, choose 0. 4, choose 0 is just 1. So we'll have 1 cos 4 theta. So cos to the power of 4 theta. 4, choose 1. So how many different ways do I have of choosing one thing from 4 things? I have 4. So 4, it'll be cos cubed theta, and then we're multiplying that by I sine theta. So let's just take our extra steps here, working these things out. 4, choose 2. So 4, choose 2 gives me a value of 6. So we have 6 cos squared theta, and the I sine squared theta becomes minus sine squared theta. So I squared is minus 1, so we get that minus sine squared theta. Then 4, choose 3 is going to be 4 cos theta, and we get minus I sine theta. So remember, I cubed is going to be minus I, because I squared is minus 1, and then we multiply it by 1 again. And 4 choose 4 is just 1, and that's going to be minus 1 by minus 1, which is just 1. So we just get sine to the power of 4 theta. So let's just simplify and kind of tidy this up a bit. We get cos to the power of 4 theta plus 4I cos theta sine theta minus 6 cos squared theta sine squared theta minus 4 cos theta sine theta. Let me see, I'll just try and add this on at the end, plus sine to the power of 4 theta. Now, what we want to do at this point is we want to kind of group together anything that has an I and anything that doesn't. So essentially the real parts and the imaginary parts. So we have cos to the power of 4 theta. Here it has no I part. This part here also has no I part. And then have we got an I part with, have I lost an I along the way there? I have an I in this part that I haven't included. So we have got an I part there. Okay, so that's perfect, and we haven't got an I part on the last section. So let's just kind of group those bits together. And then if we consider the imaginary parts, that's going to be this part here and this part here. Okay, so first of all, we're looking for sine 4 theta. So if we look at our original expansion here, that's going to be an imaginary part. So let's equate those parts. So we get sine 4 theta equals to, and we can take, we're not including the I part, so we're just taking everything except the I parts. So this part here, minus 4 cos theta sine theta. And if we look at our question and what we were asked to prove, we were asked to prove that sine 4 theta equals 4 cos cubed theta sine theta minus 4 cos theta sine cubed theta. And that is exactly what we should have there. I just forgot to put in the cubed here. Whoopsie daisy. Okay, there we go. Lovely. So we've got that part figured out. Now we need to look at the cos 4 theta. Okay, just making sure. It's always good when the question gets you to find an answer because it helps you see if you've made any mistakes along the way there. But a good one for us to see to make sure with our binomial expansion that we are checking every part of it. Okay, cos 4 theta. Cos 4 theta, we're taking all the real parts. So cos 4 theta is going to be equal to cos to the power of 4 theta minus 6 cos squared theta sine squared theta, and then plus the sine to the power of 4 theta at the end there. So we're taking all of those parts and we're going to be kind of including all of those together. Now our end result we want is that 8 cos to the power of 4 theta minus cos squared theta plus 1. So we don't want any sine parts at all. We don't want to have any sine parts at all. So we're going to have to consider how we're going to eliminate those. And the main way we're going to do that is using that identity we had earlier. Sine squared theta plus cos squared theta is equal to 1, which means sine squared theta is 1 minus cos squared theta. Okay, sine squared theta is equal to 1 minus cos squared theta. So if we kind of apply that, cos to the power of 4 theta is perfect, minus 6 cos squared theta, 1 minus cos squared theta. And on the end here, we'll have 1 minus cos squared theta squared, because sine to the power of 4 is the same as sine squared squared. Okay, so that's perfect. Let's continue working this one out. Cos to the power of 4 theta minus 6 cos squared theta plus 6 cos to the power of 4 theta. And then working this part out, we get 1 minus 2 cos squared theta plus cos to the power of 4 theta. So if I kind of group like terms together, I get 8 cos to the power of 4 theta minus 8 cos squared theta plus 1. And is that what we're looking for? That is what we were hoping to get. So that is our end result for that one there. So there's kind of a lot of work for what can seem like maybe little payoff. For one like that though, it's always nice to get a question where you're kind of working towards a particular answer because it gives you an idea of if you've kind of been heading in the right direction. So let's just see maybe some of these practice questions. So these are kind of smaller ones, but looking for the same idea. And it can be, these ones can be kind of tricky. So if we look at expressing sine 2 theta in terms of sine theta and cosine theta. So again, we're looking at power of 2. So we're going to be looking at cos theta plus I sine theta squared. and the two ways of doing that out. So if we use De Moivre's theorem, we get cos 2 theta plus I sine 2 theta. If I was to expand using binomial or just by multiplying out the bracket, whatever we do, we get cos squared theta plus 2I sine, so 2I cos theta sine theta plus sine squared theta. Or sorry, not plus, it'll be minus. It'll be minus sine squared theta because we're squaring that I part as well. So I squared is minus 1. That's perfect. We're looking at sine. So again, we're looking at the parts that have i's. So it's going to be this part and it's going to be this part here. And we're going to get that sine 2 theta is equal to 2 cos theta sine theta. And that's one of our double angle formulas that we had from trigonometry. So sine 2a is 2 cos a sine a. We had that already. But it's just good for us to see kind of a way that we can derive that or prove that in a sense. Looking then at cos 3 theta, so same idea again. So if we use De Moivre's theorem, it's going to be cos 3 theta plus I sine 3 theta. And then on the right hand side, I'm using my binomial theorem. So for multiplying that out, it's going to be 1 cos to the power of 3 theta plus 3 cos squared theta, and then multiplied by I sine theta. Okay, plus 3 cos theta I sine theta squared plus 1 I sine theta cubed. Okay, so let's just work out those values here. So the cos 3 theta obviously will stay the same. Here we have plus 3 I cos squared theta sine theta plus, let me see, so when we square that I sine squared theta, that will become minus, so minus 3 cos theta sine squared theta, and at the end here, minus I sine cubed theta, so minus I sine cubed theta. Now we're looking for cos 3 theta, so we're going to be looking at the values that have no I part, so the real parts on each side. It's going to be this part, and it's going to be this part here. So let's just equate those. So cos 3 theta is the same as on the right hand side, cos cubed theta minus 3 cos theta sine squared theta. So cos 3 theta is cos cubed theta minus 3 cos theta. And we don't want to have any sine squared, so we're going to use that same identity we used the last time. Sine squared being equal to 1 minus cos squared. And then we can just simplify and hope that we end up with the same format that they are looking for. Minus cos 3 theta plus 3 cos cubed theta. And simplifying the right hand side, then we get 4 cos cubed theta minus 3 cos theta, which is the format they were looking for. So with these multi-angle ones, it's just about really taking it slow and steady through, comparing the real parts and imaginary parts and imaginary parts. And we saw that in the equality section when we were kind of doing those comparisons already. The other key thing to watch out for with these ones is that I squared part, or I cubed, the powers of I. And again, that's something we've looked at earlier as well in the chapter, but it's just making sure you don't forget about them, okay? Because you can see even there myself doing the examples, it's very easy to forget about them and forget about that binomial and keeping your powers the same. There's a lot of moving parts here, so it is just taking it nice and steady to make sure that we're hitting kind of all those beats that we need to allow us to kind of get the desired format and get the desired results.